In this video, we will discuss about Beckmann rearrangement. So in the Beckmann rearrangement, you have an oxime. So this is the oxime. And if you treat this with an acid, so this will undergo Beckmann rearrangement. In this case, you will generate a 7-membered ring. We can call this as caprolactam. Before understanding the mechanism of Beckmann rearrangement, let's have a look how these oximes can be synthesized. So I'm taking here an aldehyde. And I treat this aldehyde with hydroxyl amine. So you will eliminate one molecule of water from here, and what you will generate is an aldoxine. This is because you generate this from an aldehyde. So if I take a ketone and if I treat with the same reagent, so what I will get is a ketoxine. Because we started with a ketone. In general, the aldoximes and the ketoximes can be called as an oxime. So if you have an oxime, and if you have a dehydrating agent, for example, the sulfuric acid, or even you can have the PCl5 or POCl3, so they are dehydrating agents. This means that they can remove water. So the first thing is like you are converting this OH group into a better leaving group by treating this with a dehydrating agent, right? So you have the acid here. So the acid will protonate this OH. So you have the sulfuric acid like this. So the lone pairs of oxygen can now take this hydrogen and it will form this O minus here. So what you will end up is you will generate this one and the anion of your sulfuric acid will leave, right? Like this. And now you converted your alcohol into a better leaving group. So now this can leave us water and you will generate a positive charge on the nitrogen. As you know that the nitrogen is an electronegative element and it is not so happy with a positive charge on it, right? So what is the only possibility? This can neutralize this charge by migration, right? So this will undergo a migration here, or it can go this way as well, right? But this compound is symmetrical. So if both the sides are like going migration, you will get the same product. So let's consider you are migrating this side and you will generate a positive charge on this carbon. So what you will end up this one and you have a positive charge on this carbon and you are generating a 7-membered ring, right? So now you have a positive charge on your system. So it can behave like an electrophile, right? So if you have a suitable nucleophile in your system, this nucleophile can attack the electrophile. So if you see the nucleophiles, you can see that you have the water in your system, right? So the water whose lone pair will attack this positive charge here and it try to neutralize the positive charge. So what you will get, so you will get like this with a 7-member ring and this is neutralized and you will end up with a positive charge on your oxygen, right? Now if you see the anion of your sulfuric acid that you generated previously, so it is ready to take a proton and regenerate the acid, right? So you have this one. So I'm calling this as HSO4 minus, right? So this can take this hydrogen and it can neutralize the positive charge on the oxygen. So what you will get this 7-member ring here, right? And you are converting this into OH. So now this is very easy. This can undergo tautomerism. So the lone pairs on the oxygen that can jump here and this will go to the nitrogen. So what you will generate, the nitrogen with a negative charge here and the double bond becomes single bond and you are generating a double bond O plus H here, right? And you are generating the 7-member ring. So the last step, this negative charge can take this hydrogen from here and it can neutralize this one. And what you will generate here the NH, and here this is a ketone and you have the 7-member ring. So this is our caprolactam. Suppose this intermediate is unsymmetrical. In this case, we have to know which group is migrating. So in the next section, we will discuss which group is migrating in an unsymmetrical intermediate. Suppose I have taken an unsymmetrical oxime. So here I am taking an unsymmetrical oxime, which is actually an aldoxime. And if I treat this with an acid, so you will eliminate this OH as water molecule, right? And you will generate an intermediate like this with a nitrogen containing a positive charge. So here you can see either the CH3 group can migrate to the nitrogen or the hydrogen can migrate to the nitrogen. So let us consider the two possibilities. Suppose if the CH3 group is the migrating group, then what you will get? You will get the nitrogen with a CH3 here, and you have the positive charge here, and you have the hydrogen. Or if the hydrogen is the migrating group, so what you will end up is with you have the hydrogen here and your CH3 and you have a positive charge. So if your oxime is unsymmetrical and you have to understand which of this group is migrating, okay, so you have to see the stereochemistry of your starting material. So if your starting material is unsymmetrical and if the stereochemistry of the OH is mentioned, then the migration will happen to the group that is anti to the OH. So we can call it as anti, or we can even call it as trans. So if the stereochemistry of your starting material is mentioned, then the migration will happen to the group that is anti to the hydroxide group. So in this case, this will be the pathway. So what you will generate, so you have the NCH3 here, right? And you have a positive charge with a hydrogen, right? And this can be attacked by the nucleophile, that is your water. So the water can attack and neutralize this positive charge. So you will end up with here NCH3 and you have the OH here and you have the hydrogen here. This can then undergo a tautomerism like this and you will get the final product here an NH3, CH3, and you will generate a carbonyl group here, right? So this is your final product. Suppose in your question, if the stereochemistry is not mentioned, then what you will do? So in that case, you have to follow the migratory aptitude. The migratory aptitude. So the migratory aptitude, hydrogen have the higher migratory power, then comes the phenyl, then comes tertiary, secondary and primary. But you have to remember, in the case of Baeyer-Villiger oxidation, if you take the Baeyer-Villiger oxidation, in this case, the migratory order is first the phenyl will migrate, then hydrogen, then tertiary, then secondary, then primary. Another case, this will be the migratory aptitude. Okay. So if the stereochemistry is not mentioned, in that case, you have to follow this migratory aptitude order. Let's solve some other problems to make your understanding much better about this topic. So I'm taking here an oxime, so which is attached to a hydrogen here, and you have this one. And if you treat this with H2SO4, so what will be your product? So the first step, if you treat this with H2SO4, you will eliminate this OH into water, right? So what you will generate? So you will generate this intermediate. You have the carbon, here the hydrogen, and you have the nitrogen with a positive charge. Then you have to know which of this group is migrating. So according to the migratory aptitude, you have the hydrogen, then phenyl, then comes the tertiary, secondary and primary carbon, right? So the hydrogen has the higher migratory power. So in this case, the hydrogen will migrate to this position. So what you will end up? You will end up like this with the carbon here, right? And you have the NH here, and this will take a positive charge, and this will be attacked by the nucleophile. So I'm not going to draw the complete mechanism. You can draw by yourself. So the final product will be, you will have the phenyl here, right? And you will generate the carbonyl here, and you have a NH2 here. So this will be your process. So we can try another example. So you have a cyclohexane here, which is attached to a cyclobutane, and you have an oxime, right? This is a ketoxine because both side is an R group, so it is a ketoxine. And if you are given that this is treated by ECl5, right? So this is a dehydrating agent. So the first step is the same. So you will end up with a nitrogen here with a positive charge, right? Then next step, you need to know this is migrating or this is migrating. So if you take this carbon, which is attached to how many carbons? So here one and here one. So this is a secondary carbon, right? And if this carbon, if you see, this is attached to one carbon here, another carbon here, and another carbon here. So this is tertiary carbon. So the migratory order is tertiary greater than secondary. So this will migrate to the nitrogen. So what you will end up like this, right? And this bond will migrate. So you will generate a 5-membered ring. So you can get the final product like this. Okay, so this is the final product. And let's see one more example. So you have here the oxime. Okay, so this is similar to the first questions in this video. And suppose if I make it unsymmetric by attaching ACH3 here, and if I treat this with sulfuric acid, so what will be the product? So you can see here, once I treat with the sulfuric acid, what you will generate? So you will eliminate the water and you will generate the nitrogen with a positive charge, and you have the CH3 here. So now you see here, this carbon is the secondary carbon, right? And you can have this as the tertiary carbon. So again, the tertiary greater than secondary. So what will happen? This carbon will migrate, right? So this carbon will migrate. So what you will get? You will get the final product NH here, and you have the CH3 here, and you have the carbonyl here. So this will be the final product.